I'm talking, you can turn off microphone because it's too noisy. Okay. Okay. I explained it to you that
the noise from my
yeah,
microphone.
yeah, it's coming from there. Yeah. Yes, you can turn off when when I ask you a question or something. You can turn off. Okay. No, what I asked you was that just to go through the physics of the Bose-Einstein condensation and back to me. The fact which I shared with you before about the analog between the energy and the money in the market, that doesn't mean that if the energy is quantized, so money should be quantized. I think you didn't get the point. The point was that they have a similarity. I mean, if you identify, as I told you, money with energy, you have ensemble. So what is the ensemble? Ensemble is a system, is actually a collection of many systems, and all members of this collection are the same. So I mean, you have, for example, a large number of the free particle, a large number of the harmonic oscillator, or whatever. Each ensemble could have a continuous or discontinuous energy spectrum. I mean, for example, if you consider a collection of the free particle in the box, so the energy of the particle in one-dimensional box is quantized. I mean, between two energy, there is no any other energy. You have to pass from level 1 to level 2, from level 3, and there is nothing like level half, or level 2 half, or level 3 half. This is called a quantization of energy. But there are also systems which energy is not quantized, so energy can extend it from up to any levels. Like, for example, just consider these free particles not in very low temperature. So if you consider the particle in not very low temperature, then you can see that the behavior of particles is fully classical. It's fully classical, and okay, do you hear me?
Yes.
Okay, because internet dead. Okay, so just go to the level of in the system when the temperature is not very cold. When the temperature is not very, very cold, then the quantum effect will be ignored. So you can consider the particle like a semi-classical or classical. So instead of the quantization, you have a continuous spectrum of the energy. I mean, energy will be proportional to p square. When energy is proportional to p square, so for each p you have energy. So there is no worry about the discrete energy level or energy levels in general.
But for
All right.
boson, does it work with
Okay.
the boson?
No, it doesn't. What does it doesn't work? So bosons are the particles which we consider here without any interactions. They are free bosons. They are free bosons, and you didn't consider any box for them. So I mean, you have it with the bosons. They are in the container. The container volume is V. The number of boson is N. And you just keep the thermodynamic limit. I mean, the ratio between N and V. You fix it this ratio and allow the N and V to increase up to any numbers as you wish. Then in thermodynamical limits, so there is no any argument about there is a quantization of energy or something. So the bosons are free bosons here. In quantum mechanics, if you have a free particle and you have a bond state. Do you know what is the bond state in quantum mechanics? What is the difference between bond state and free or unbound state in quantum mechanics? Do you know?
Bound state, which is near to the nucleus.
No, give me one simple example. If somebody asks you, for example, the electron in hydrogen atom is bound or is unbound?
Bound.
Of course it's bound, because you have a Coulomb force. That is the reason that the electron is subjected to the Coulomb force, and it feels the interaction with the proton or with nucleon.
The
What
same
about the
one.
unbound?
Is it the same for when we said free electrons and not free electrons?
Basically, there is no any free electrons in the nature. We never can find any free electrons. But for example, in photoelectric, do you know what is the photoelectric effect? Do you remember?
When there is an ejections of the electron, which is
Which
far away.
which electron? It is
As
free electron or
no
bound electron?
free electron, which is on the outer shell of the atom.
Why it happened? Why the electron is free? It is not real electron. It's not a real free. The fact which happen, the things which happen here is that the photon which emitted from the source and observe it or attack it, the outer electrons has more energy. I mean, it has energy enough to take the electron from the surface and give to electron, not only take it, so it also gives to electron a little kinetic energy. And that makes electron like a free particle, so electron can jump. Otherwise, the electron has some energy, which this energy bonded the electron to the surface of place. Anyway, for Bose-Einstein systems, you are dealing with free bosons, okay? Free bosons. So that is the reason that I told you the mechanism of the Mach
Doctor, I cannot hear you.
All right. Do you hear me now? Hello, do you hear me?
Yes, now okay.
Okay. I have to remove the mic, the headphone, so that's the only things I can do to have a better voice. Okay, anyway. I have to still you see my screen or no? No, you don't see.
Yes, I see.
I will share again. You are present. Okay. Let's go, and today we want to little bit familiar with the concept of the economic physics, just the important words, and then we will study. We will go to study the example which solve it as the occurring of the Bose-Einstein condensations in some spatial economical systems and the comparing the phase transitions with the financial crisis. I send you one paper as a review articles for economic physics. So we go page by page by that. First of all, I want to mention that the economic physics is a subject just in 1990 proposed. And this is about the distribution of money, distribution of money, distribution of the wealth, and whatever is related to the money and wealth. This is the main problems. So they wanted to know how the money and the wealthness will be distributed over a community. We know that the system of particles and human systems have a different, very different. They are very different, but if you talk about the distribution, actually, I want to tell you that the distribution of money, for example, or distribution of wealth in the community have something to do with the distribution of the energy, for example, in some bosonic systems. So this is what they will ask you when you wanted to do the first presentations to the department. They will ask you what is economic physics. So you can say that economic physics is a subject which is developed in 1990 and is a merge between the technique of the statistical physics and the concept of the economy. And the main problem is that to know how the wealth and the money and whatever is distributed and how we can study those distributions, like what we do when we are studying the distribution of the energy or something else in the statistical physics. So the subject is related to things which we call it complex systems. Complex systems are the systems which the number of degree of freedom is too much. We have so many number of degree of freedoms. Do you remember what does it mean, the degree of freedom?
It's related to the potential energy.
No, in general, in physics. When they call what is the degree of freedom, what does it mean? For example, a pendulum, you know what is the pendulum. So pendulum is hanging from a point and it started to make oscillations. How many parameters you need to write down the equation of motion for these oscillations? How many variables you needed? The pendulum.
We need to.
All right, what is important in pendulum is that you needed to know that simply you need just one parameter, and the parameter is that the angle which sweep by the pendulum during the time periods. theta, for example. If you know the theta, then you can write the Newton law, or you can write the Lagrange-Euler equations or whatever in dynamics. And by solving those equations, you can tell me that what is the period of pendulum, yes? Or after
Yes.
some time, or after, for example, how many seconds the pendulum will complete a complete oscillation, huh? One oscillation, two oscillation, and this. You don't know this. This is the physics one, actually. Just the word is
So,
different. Call it the number of the. So do you hear me? So as I mentioned, the number of the variables you needed to describe the dynamics of the system is called degree of freedom. In economophysics, you are dealing with so many parameters. Like, for example, if you are going to study the stocks markets, you know, the change of the price in the stocks markets or change of the rate in the price of the,
Victor,
yes.
you mean that's for example, for ideal gas energy. We need the volume and the pressure and the
No, no,
temperature.
no, 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 no. Those
So
are, no, you're confused. This is called intensive parameter and extensive parameter. This is, we call it intensive and extensive. I mean, to describe the thermodynamics, you need to know some parameters which they are changing by changing the size, or you have to know the parameters which they are not changing when you change or increase or decrease the size of the system. This is called the first one is called intensive, and the second one, if doesn't change, if change, is called intensive, and if it doesn't change, if it doesn't change, we call it intensive. And if it change by changing the size, it's called extensive. No, the degree of freedom is the number of the variables you need to describe your system. In economophysics, for example, you're going to talk about the change of the rate of the price of some things. Change of the rate of the price of the food, for example. During a time, by many reasons, the price will change. Yeah. For example, even the political crises or political battles, they will change the price. Remember, for example, if something want to export it from the China, for example, to a state, for example, and if the government decided to make a huge tax on the import goods from the China, then you see the price will be changed immediately. I mean, the change of the price will be very, very high. Yeah. So there are so many parameters, like I told you, the politics and many other things. So that is make life is very hard, and this is leads to the concept of complex systems, many degree of freedoms. Okay, one of the main things. So economic physics mainly are trying to explain the distribution of money, wealth, or to study and predict the exchange rate or the price of the goods, or even trying to predict the change in the stocks market. For example, you have some money, you wanted to spend your money in the stocks market. Okay, in stocks market, you every day see the change of the stocks prices. For example, I will show you now the sample. Look, for example, here, I will show you. I hope you see. I don't think you see that. For example, stocks September to if you are going to the tradings, for example, stocks rate. For example, if you make it the world of stocks markets or stocks rate, September 2020, 29 of September, you see you find so many things. For example, you can see that the first questions, which also this is your questions as a person who want to enter the market, is that is September a good month for stocks or not? Huh? In many countries with weak economy, mainly, the money which the people spend in their markets, I mean in stocks markets, is a source of the financial support for the government, as you know. Yeah. So
Yes.
if the people spend their money in the stocks market, and if all the people lost their money, it may happen several times, it happened in the history, then it will be tragedy actually for those people. But the container or the reservoir, I mean the government doesn't change it. If the stock market is related to the government, so they will get the benefit. So you see that this is very difficult to enter a market even if you have money. Econophysics is trying to give you the distributions, the change in the stock's price. For example, stocks there is always a change in the, you see this is you see that here, for example, it is show that the different stocks, how they change. For example, it gives you the rate of the change, for example, for Bitcoin or dollar of United States comparing to the dollar of the Canada, for example. The ratio is 1.3 and it is reduced, for example, with 0.08% just recently. And okay, tell me next week how much it will change. We don't know. Answering such questions and giving the predictions is one of the tasks of economic physics. And also to find, and also, okay, and predictions. So one of the things which is very important, I think it was one of the first things which the people study, was that the fluctuation in the stock's price and exchange rate. So the things which happen here is that actually stock price, for example, if you call stock price, for example, this is what I show you. For example, the ratio between the change of the exchange rate, for example, $15 of the United States and dollar of Canada, or the Bitcoin, or British Petroleum, for example, or the West Gulf, for example, oil, or whatever, a Gulf oil, for example. You know, each one has a price, and this price is always changing. For example, if something happened in this region, for example, if some conflict of interest or military conflict between countries, so this price will be changed very quickly, or increase it or decrease it. It depends. It depends. In Corona time, for example, you know, the price of the oil decreased significantly because no one moved. No oil was transferred or imported. All the car at home, so no need the petrol, so no need one. No one need benzene. So this is that happened. This is, for example, a sample of a type of the stocks markets. For example, you see, we always have a time series of the one quantity during the times. This is show, for example, the change of the a quantity which call it SP500. It's something related to the stock market versus the time actually. And you see in sometimes by looking under this graph, you see that you see the peaks and sometimes very sharp peaks. And sometimes you see a little bit more stability in the markets. But those market is very, very fluctuating very fast. The other one, for example, is the time series for the returns. For you put your money in the market and you do some tradings, so you expected some return money, yes? With the 1,000, you expected first month you earn, for example, 1,050. So 50 will be your return. So this graph which you see here is the return fluctuations. What does it mean, fluctuation? Fluctuation means that the change in the very tiny period and very quickly change. So this return diagram, for example, show you how much people earn. You see that, for example, of course, it depends to the type of the data. For example, you see in the short period, like 10 minutes, sometimes the people have a great return. I mean, they earn a lot just for the short period, you see. But if you look at for the long behavior, the Gaussian is the long. If you look for the long behavior in the long time, it seems that this trading or this market is not a good market for you. Why? Because the rate, because the fluctuation of the returns is almost zero. You see here? So in short times, 10 minutes, not 10 minutes actually. It is because we are talking about the years. We are talking about the years from 1960 to 2000 for 40 years. So if you wanted to take this 40 years, like 1 hour, for example, just make it a scale. So 40 years, 10 minutes of that will be 1 hour 6, so 7 years. It showed that in the 7 years, if you study somewhere, you earn a lot, but during the whole period, you didn't earn very much. Okay, do you have any question about this?
Victor, this is what is related to the adiabatic change and the physics.
This will be related to the fluctuations. You remember we talked about the fluctuation in the first lecture, I think. Fluctuation of energy, remember, and fluctuation in the number of operators, well, N. So this is called, because we are talking about the money market, so those fluctuation are the fluctuation of the energy, actually, if you want to. And it showed that the fluctuations are very high just for short times. I mean, you can, finally, I can tell you, this market, you can just win if you are trading in the short period.
Yeah, okay.
How you can quantify this? I mean, you have a parameter. I told you, for example, this parameter is it stocks, for example, the rate of the stock. You put all your money in oil, for example, $1 million, and you are expecting that the oil price increasing. All the country in the Gulf, they are living by the oil. Actually, you expected in the stocks market the price of the oil change, and you earn and you have benefits or you have a return, good return from your. How you can quantify it? First of all, this is about the money. So money is a huge amount of the things. So instead of the working with the quantity like S at the time, you look working with logarithm. Because logarithm of million is just 6. So working with the digits like 6 or 10 is more easier to work with million or trillion or billion or something. If you think about the change of the rate of this stocks market between the period of t to t plus delta t, you see that at each time and for next time, you can read it that. For example, take delta t here in the diagrams between 1975, for example, to 1980, 1985, for example, or 3. During these 7 or 8 years, this is to take you as a delta t. Then you can read the price from here to here, and that's give you the difference between them. But as I told you, those are big numbers. So what we call it return is actually is the logarithm of this quantity. So logarithm of the stock's rate at the second time minus the logarithm of the stock's rate at the first time. So this difference of logarithms gives you the things which is called return. So one of the so if you have s as a function of time, so you can calculate it, the return. You can draw a plot the return diagrams. Just consider a table of the s versus the time and trying to draw the lns at the second time minus lns at the first time. Those are time series. So, and the fact is that many markets, when you calculate the return, in many markets, this parameter g, which is the logarithm of s at the second time minus logarithm of the s at the initial time, this quantity will have the shape of Gaussian. Everywhere, if you have a Gaussian, it means that the parameters are distributed. The parameters are distributed normally. Yeah. So these markets are good. If you have a Gaussian distribution, finally, this is a not bad market for return, for the return function. Then it shows that the market, generally speaking, is not a bad market. Okay, when the statistical mechanics comes, the statistical mechanics come, as I told you, when you want to study the, for example, the return, which is the difference between the logarithm of the stocks rate, for example, between 2 times. This it has a distribution. What is the distributions? Distributions means that between for example 2 time of t1 and t2, you can exactly tell me that how much money somebody earned or how much return this person had. So distributions are functions which they are talking about the values of the quantities between intervals. If you back to statistical physics, for example, the particles are moving with different velocities. But finally, if the particles are classical, like for example, if the temperature is not very low, then the distribution will be the Maxwell. And with Maxwell distribution, you can exactly tell me the mean value, I mean the average. You can tell me the variance or root mean square of the speed or velocity of particles. And also you can tell me that between 2 specific values of the velocity, how much particles are exist. So this is the color distributions. So in the stocks market, a little bit is difficult. So distribution are not Maxwellian generally. Distribution are these log distributions like that, and they are some power law distributions. What is this log normal distributions? Log normal distributions, I want to plot it this here to see, because normal distribution. Log normal distribution, you say that P is exponential minus logarithm x square log x. I have to correct this. Since I want to plot this, this is the log normal distribution. It looks like the Gaussian, yes, but it's not a Gaussian. Why it is log here? Because I told you we are dealing with the quantities. With these quantities have a big numbers like million or trillions. So this is called, for example, one of the distributions, which this is a distributions of the one quantity here, the return, for example, return rate versus the time. There is another distributions, for example, the power law distribution and whatever else. And there are some other, and especially I want to tell you that there is a Bose-Einstein distributions. I mean, some distributions are very, very similar to the Bose distributions. Bose distributions. So the particle distribution, so the money distribution here, X is the money or the rate or return or whatever. The distribution of the rate or money looks like the distribution of the energy of the bosonic system. This is just analog, making the analog. But there is a difference, as I told you. The difference is that we have a distribution of this quantity during the time, and in the usual thermodynamical system, we have energy versus the momentum. So momentum here plays the role of the time, for example, and whatever. We will learn this dictionary. I mean, each quantity is corresponding to the which one is. We will see that in here. All right. I told you that sometimes it's not a good idea to enter a market with the money because the market maybe fall down. So you have to be familiar with the concept called risk. I want to ask you after this lecture, go and read it exactly the page which I'm reading again, and make notes for yourself, because I'm just talking and go. Risk function is a parameter which is actually, it is nothing just the variance of the return. So return was the logarithm of the Stokes rate. So as you see, the risk is, if you want to talk about the risk between a time period, for example, from t to t plus t, for example, 1960 to 1980, 20 years. So in each time intervals, in each short time interval delta t, you have g. G is logarithm s t plus t over s t. This g, return factor. Then you can calculate the variance. Basically, this market has the average for the return. I mean, finally, during 40 years, for example, no one earned more than some money, and everybody averagely, for example, average earn around, for example, $20,000 in average. So if one person, of course, earn 500, the other one 20, the other one 3 or something. If you take the average, so the average return of these markets is nothing just like the average of velocities, for example, average of energy. So you can immediately write the quantity which is called variance, and we don't say the variance. This is what I want to tell you, that here we don't say this is a variance. We call it this risk. Risk. So risk is nothing just a local variation or variance between the period. This is the period from t to t plus delta t, 1960 to, for example, 1980. What is the mean value? The mean value of GAT in the windows. What is the windows? In economic physics, again, instead of talking about the interval, for example, the momentum between, for example, 10 MeV per C to 15 mega electron volt per C, for example, this is so 5 mega electron volt per C is the range of the change of momentum, for example, in your statistical system. Here we don't talk about the between this. We say the windows instead of the interval. We are talking about the window. Okay. And the volatility or the risk, also some people define this in different ways. So some people take the variance as a risk function, and some authors take the volatility or the risk like somehow is the sigma of the absolute value of the return rate. It depends. If you use the first definitions for the risk, because there is no any single definitions, you see, there is no single definitions. That is the activity. This is the motivation to people. If you use the variance as a risk or volatility, so then you need the average. But if you use the second definitions, you don't need the averages. But the things which happen is that it is important that whatever distribution you consider, you need to consider the correlations. I mean, for example, the price of the oil, for example, changed 1975 to 1979 during 4 years, very much changed. So many people earn, and I think the average was higher than any other time for the people in that period. No one, for example, earned in this market less than, for example, $10,000. Anyway, correlation is important. Do you know what is the correlation? Correlation means that how the average in this period is related or affect the average in future. You see, if a market has the reputation that during 5 years the minimum earning was $10,000, for example, that make a reputation for the market. So you need to know the correlations, the relation between this average with the next average and others. Okay. But I want to tell you, distribution function is universal. This is very important. This is, I think, this is the main concept. If you make a distribution function, if you consider the stocks markets during the time for different markets, it seems that the distribution function is universal. I mean, if you make this distribution function for this oil market, then for other markets, people find a very similarity. I mean, the distribution always looks like, you know what does it mean? For example, the change of the rate of the stocks market for the oil, for example, almost will be this log Gaussian distribution, as I show you. And if you consider another type of the goods in the market, they also approximately looks like that. So this is a called distribution function is universal for different stocks in different markets during different time. It's very important. That makes that make a possibility to predict the markets. This is just comparing the distributions, comparing the distribution of returns for different type of the quantities, for example. And this is also distribution of volatility, but we didn't calculate that actually. Autocorrelation. So I told you the correlation function are very important. How much one quantity will change the history for that quantity for that quantity in the future. If the oil price, for example, increases during 1970 to 1975 very quickly, how this change in the price affect the change of the pricing after 9/11, for example, or after the war in Afghanistan, for example, after the war in Iraq. For example. Predictability. There is no predictability 100% in the stocks markets because they are dealing with time series. We not exactly can tell you that what's going on in next 20 years, but we can predict it, just a little bit predictions. So the fact which make it possible to consider different distribution is autocorrelations. The autocorrelations is the study of the effect of the between the effect of the a quantity or a parameter in one time to the future of that. For example, if you consider the return, you can consider the autocorrelation for the return functions. Or if you consider the risk function, you can consider auto. For example, after the 9/11, for example, the risk for the air flight companies increased because of that. I don't know, you know little history of 9/11 that's happened. This attack to the New York, for example, increased the risk for the increase the risk of the flight for the companies during a period. So the risk in that period was increased very much. Then some effect of that risk still remained. I mean, after that times, everything changed in the airplane companies. The price of the tickets also changed because they needed to hire more security people. Yeah, they have to buy a new tools or instruments to be able to detect the terroristic attack actually in the airport. So you see that the correlation. So if you consider the effect of that during two times, this function gives you a possibility to consider the effect of one things to the that parameter in little bit more future. Calculating these correlations, it's called autocorrelations, is not very easy. So there is a need of the technique of spectrum analysis. But there are some little new methods and easier methods called developed fluctuation analysis, which it could be work if this quantity doesn't change very much. This is autocorrelations, for example. This function is plotted from some data for the G. G was the return. If you consider that, this is autocorrelations. Do you know what does it mean? The correlation decreases and somehow correlation is very random. I mean, in sometimes from 0 to 20, maybe maybe it indicated 20 years or 30 years, yeah, because we say that the time we divided time to 0, 10, 20, but this is actually years, as I told you. The 0 to 10, maybe it means 10 years. During, for example, 20 years, as you see, the autocorrelations analysis of the return show you that the autocorrelation decreases. I mean, the history of the return in that market doesn't affect or give the negative effect to the return of the future of the market. Bad reputations. Okay, are you here?
Yes, I'm with you.
The exponential drop off here in the return, for example, in the time is going to be along a parallel decrease in volatility. I mean, the risk, you know, the autocorrelation function for return decreases, and this is the graph for the risk. So you see the risk also, the bad reputation for market, it doesn't mean that the risk will also increase or decrease. It depends, but here the risk decreases in this market. That all is about the data. Okay. You want to stop it here up to this section 2.1.3 and let you go and read it the first pages, 7 page, and as a task also go through it and try to read it more and more. But I will go through this paper. I mean, the next time we will go through this paper and try to understand this paper, or maybe I will make the PowerPoint if I find the time, so the PowerPoint can be better than that. I try to make a PowerPoint and collecting all the information about EConophysics one time. So with PowerPoint, you can go faster because, you know, this is the subject is not like we solve the problem or solve the equations, or we have the, you see, we have a question, we plot the questions, but I think it's too much talking, these subjects. That's the reason I'm talking. And because this is economy, so this is a social science actually. We are dealing in the social science with the physics methods. So we don't have so much calculations, but we have something. Of course, we have some calculations later. So I think that's enough for today. You have 7 pages from this paper, wrong, and you have to start to write for yourself some notes, some few pages about what you learned so far. Then if you share those information with me, then I will see that. Yeah. Yes. What you want?
I wrote.
Good. Okay.